University of Limerick, part of the Dibanet proposal. Very happy to be here in Thessaloniki. It's some 10 degrees Celsius back in Ireland at the moment, so this is quite a pleasure for all of us here from Ireland. We'll talk to you a little bit about levulinic acid production from lignocellulose biomass. As JJ said, this is part of a European project, and in particular, I suppose UL's input to this project is to look at acid hydrolysis as a means of converting particularly the cellulose fraction of lignocellulose materials into this material called levulinic acid. We'll talk a little bit about Carbolea, which is the research group that we have in operation in the University of Limerick. That's part of this. Conversion to levulinic acid is not our only activity. We also have some activities in pyrolysis, but this talk will be specifically related to levulinic acid production. The context in terms of what are the limiting factors in terms of these conversions, and in terms of Dibanet, what we've actually achieved is we've come up with a new process or a new design for the conversion of levulinic acid, and we're quite happy that the EU seems to be pretty much convinced that it is a way forward. In terms of the Carbolea group itself, obviously we have various lab-scale reactors that we use to do our experiments. But we've also, I suppose, endeavoured as well to try and migrate to a more, I suppose, what you would call lab pilot scale type systems, where we can take the research that we do in the lab up a level to look at some of the engineering issues connected with trying to take our research into the real world. And in that regard, we have some useful units, which may be of interest to anybody interested in collaborations in the future, where we have actually built continuous systems that process 6-7 kilograms of biomass per hour. This is just another view of those. Levulinic acid, what is it and why is it important? Well, it's a molecule which can be converted through a hydrolysis process from ultimately from glucose, but obviously in the case of the sustainable energy we want that glucose to be derived from the cellulose fraction of biomass. Why is levulinic acid interesting? It's interesting because as a platform chemical it has a lot of interesting organic chemistry functionality. So it has both a carboxylic acid group and a ketone group. And it's not necessarily the levulinic acid itself that we're interested in, it's what we can actually make from it. Victor will talk to you in a little bit about his end in the Dibanet project, which relates to catalysis. And what is interesting about levulinic acid is from this material we can create all sorts of interesting platform fuels up as far as C9 hydrocarbon. The other main reaction within the lignocellulose material that we're interested in is the conversion of the hemicellulose fraction, which releases C5 sugars like xylose, to the compound furfural. And again, furfural in and of itself is quite a valuable product. It's used as a solvent in all sorts of organic synthesis reactions. And the difficulty of trying to obtain both of these materials from a lignocellulose starting substrate is, of course, that we have a very heterogeneous material going into the reactors, and we have a lot of undesirable reactions that can happen. Particularly, we have a lot of interference from the lignin. Lignin itself is a hydrophobic material, so it infers what we call recalcitrance on the starting substrate. It makes it very difficult for our chemicals, our acids in our hydrolysis process to access the cellulose components themselves. We have a lot of parallel reactions that can happen, particularly the formation of undesirable carbonaceous material, which are generally all lumped into this heading of humins. And we have to try and optimize the production of these materials by obviously selecting appropriate reactor configuration, temperature and processing conditions. When the Dibanet project started, we had originally intended to, I suppose, look at the current state of the art at the time was a process called the biofine process, which involved acid hydrolysis at very, very high temperatures in a two-stage reactor system. We had a first stage reactor which operates at 220 degrees, very short residence time. The biomass is chipped up, it's fed in usually at about 5% load, and the first stage we flash off, or we're supposed to flash off furfural. In the second stage we have a reactor that's operating at a lower temperature, about 200 degrees C, and residence time of about 30 minutes. And it's in this reactor that we facilitate the conversion of the glucose or the cellulose fraction to levulinic acid and indeed formic acid in equimolar amounts. One of the problems with the biofine process is that the lignin fraction of the biomass and indeed the hemicellulose fraction of the biomass do not particularly like these reaction conditions, and they're generally carried through the process and come out the other side as a waste, what we call an acid hydrolysis residue. So when we looked at how we might improve on this process, I suppose the key areas were in terms of the actual hydrolysis of cellulose itself. It is a very, very energy intensive process, mostly by virtue of the fact in the context of a lignocellulose biomass that the lignin is hydrophobic and it infers its recalcitrance on the starting material. We have multiple components. We have a very heterogeneous mixture of materials going into a reactor. Each of the main three components, the lignin, the hemicellulose, and the cellulose, require three very different sets of reactor conditions, of optimal conditions, to get the desired products from them. Particularly the furfural is not stable under the process conditions that are optimal for the processing of cellulose. It's very, very energy intensive. We have very, very low throughputs in terms of the biomass. Obviously, 5% loadings is we would like to do better than that if we could. And in terms of scalability, using very high pressures is obviously not desirable. So within that context, I suppose we asked ourselves the question, was there a mechanism to reduce the mechanical and energy inputs connected with the grinding of the biomass? Typically to get into an Arrhenius, get into a regime where your kinetics are purely Arrhenius and take mass transfer out of the equation, you have to chip the biomass down to below about 800 microns. Could we reduce energy inputs and increase the yields, etc., and all the things that you would like to do in terms of improving a process for the production of levulinic acid. One of the things that we arrived at to facilitate that was a pre-treatment process which we've have filed a patent on in the University of Limerick as part of the Dibanet project. And what we had seen is that the pre-treatment was a feasible means to fractionate the biomass, so we could separate out the cellulose stream, and then particularly the cellulose, instead of being trapped inside in the middle of the lignin that's part of the structure of the plant, was actually rendered to a very, very high surface area form that was highly accessible and highly amenable to hydrolysis. We also could, by virtue of the process, remove the lignin and also convert in the same step the hemicellulose component to the monomeric sugars. This system was autothermal, it didn't require a huge energy input, and the resultant cellulose we found was 10 to 12 times more digestible. These are just some exemplary results. The comparison of the green is the raw material, the chipped raw material, with the red, which is the pre-treated miscanthus. As you can see, the yields of levulinic acid that are achievable is much, much greater. Same way, if we increase the acid, we have a comparison of the blue and the black. We also found that the pre-treatment was very, very good from the point of view of enzymatic hydrolysis, and in terms of enzymatic hydrolysis, generally the limiting step is the release of glucose from the cellulose itself. And as you can see here again, this is the raw material, and we have an increase of 10 to 20-fold in terms of glucose release by virtue of applying our pre-treatment to the starting material. This then, we decided, would form the basis of a design proposal for a new method to acid hydrolyze cellulosic biomass to give you levulinic acid. And the basis of the design is that we apply the pre-treatment first, and that gives us two streams. One is a very cellulose-rich sludge, which is fed to acid hydrolysis. The other is a formic acid liquor with dissolved C5 sugars and lignin. And from this formic acid liquor, we can actually recover the lignin and also convert the C5 sugars under an optimal set of processing conditions to furfural, which can also be recovered. The cellulose then, instead of being sent to a high pressure reactor, is sent, because now we have reduced the recalcitrance and made the material more digestible, is sent to a series of CSTRs operating at lower pressures and lower temperatures. This is kind of the basis of the design, and we'll just go very, very quickly through it. We have our biomass coming in here. We have a pre-treatment reactor which we've designed, and we mix in hydrogen peroxide, and we have a formic acid stream as well coming back from elsewhere in the process being recovered. From that we get out three streams. One is an oxygen stream, a gas stream. One is the liquor stream containing the C5s and the lignin, and the second is a cellulosic sludge. That goes into a second reactor. The purpose of this reactor, if we follow through the liquor stream, is to facilitate the conversion of the C5 sugars to furfural. We've generally found that being a dehydration reaction is not favoured by water, and you do need to add water to the system to precipitate out the lignin, so it's generally better to do that before you precipitate out your lignin. You have various filtration steps to clean the liquor of unreacted materials and also of the undesirable condensation products that you inevitably form in any of these systems. The material is concentrated, the clean liquor is concentrated. We add in a water stream which is recycled from elsewhere in the process, and at this point we precipitate our lignin, which is sent to be dried, and that's recovered as a product, and that is indeed a very valuable byproduct of hydrolysis. We have a stream containing mostly water, formic acid and furfural, and that then is sent to a recovery process to recover both furfural and the formic acid. In terms of levulinic acid production, and this is where we've gone beyond what was there when we started the project. We have the cellulosic rich sludge coming down from our pre-treatment, which we feed into not a high pressure reactor but a series of CSTRs, and by virtue of the properties inferred by the pre-treatment on the cellulose, we can actually operate at lower temperatures and at higher mass loadings and achieve essentially very, very good conversions. Through this series of CSTRs, we convert our materials, our glucan content or our cellulose content into levulinic acid and formic acid. We have various flashing steps to take down the pressure and also to recover some formic acid and water, which is sent up again to another process for recovery and recycling. We go into a clarifier again to clean the hydrolyzate of the undesirable products, the humic materials. And from that step then we go into a levulinic acid recovery process, which is basically centrifugal extraction using MTHF as the organic solvent. The partition coefficient of levulinic acid across MTHF and aqueous systems is roughly about 5, which is not ideal, but it is the solvent of choice that's there at the moment. And this is an area that we continue to work on and continue to try to improve, is the actual recovery of the levulinic acid. It goes through various stages to recycle the acid and recycle the MTHF, and eventually we do get out levulinic acid as a product at the end. But the furfural and formic acid recovery is a huge, I suppose, cost element in terms of when we look at aqueous-based systems for the processing of biomass. The recovery of products is always going to be an issue. But there are means to separate water and formic acid. This is a high pressure column that operates at 3 bar, and under those conditions formic acid and water form a positive boiling azeotrope, which allows us to concentrate the formic acid in the bottoms and send it back to our pre-treatment for reuse. The furfural is sent into a second process, which is pretty standard industrial process, to recover the furfural in the decanter and recycle again a water stream back to the other elements. One of the key scientific objectives of Dibanet was to come up with a process that would yield a significant improvement in terms of yields of levulinic acid over what we had initially set out to, or initially what was the current state of the art in terms of acid hydrolysis to produce levulinic acid, and that was the biofine process. One key difference is that the biofine process obviously has to chip the miscanthus, or pre-treatment we do not. And this high pressure reactor is operating at 220 and this one at 200. This part is all the same, and we modelled both of them in Super Design Pro to make sure that we were comparing like with like. And in terms of what we actually managed to achieve during the course of the project, as you see here, when I compare our new process, the Dibanet process, with the biofine process, we get much higher levulinic acid yields, an improvement of approximately 22% over and above the biofine process. And the key significant difference is actually the increase in the yield of furfural. In our case, we're getting out about 15.1 kilos for every 100 kilos of biomass processed, and that's a 69% improvement over what was originally achievable with biofine. The other key element of our process is we recover lignin, and we recover a very good quality lignin from the process. In the biofine process, that material goes through the reactor. It's highly degraded by virtue of the process and goes out with the waste as acid hydrolysis residue. By virtue of the fact that we have increased yields of the desired products, our acid hydrolysis residues, we're sending out about 23 kilos, as opposed to the biofine process, is up against 60. As part of our collaboration with CERTH, Angelos is looking at the gasification of these materials, and that's a collaboration that we're very happy with, and it's going very, very well. A comparison in terms of energy, the levulinic acid production and recovery, our process is much lower energy. Obviously, we're operating at lower temperatures, so there's a big effect on that, so we don't have to heat the recycled solvents back up to the same temperature. And also, because we're working at much higher mass loadings, we're using less solvent in general through the process. Furfural and formic acid recovery is quite an intensive energy step in the process. Our usage is somewhat higher than the biofine, but that's generally because we're recovering more product. And this again is an area where there is room for improvement, and we have some ideas on how we might do that going forward. But overall, our process compares very, very favourably with the biofine process. In terms of, I suppose, the economic evaluation of it, these are kind of some preliminary numbers in terms of costs in, costs out. One of the key elements of our process as opposed to the biofine is that we do have an additional input in terms of the hydrogen peroxide. So we need to look at how that actually affects the economics of the process. Is it actually worth doing? And if you look there, when we sum up the costs versus the increased yields that we get out, it more than covers that's 33 down there in the corner, and you can't see it there at the moment, but it's about 50% of that. I suppose once we go beyond, I suppose, what you call pilot lab scale, one of the questions that we do have in relation to our process is if we move to very big scales, can we move these materials into a high pressure reactor at volume? And the answer is yes. We've sourced the pumps that are out there to do that, with these solid dosing pumps, which are designed for the mineral industry, for their use to pump essentially aggregate slurries at up to 65% sludge, and the pressures up to 150 bars. So we don't envisage that will be a limiting factor in terms of scaling up our process to a ton per day or thousands of tons per day process. We have built the pre-treatment reactor. We've just recently built this one. It's in addition to what we had originally built in the Dibanet process, and we're just about to the point of testing that at scale. And that's it. Thank you very much for your attention.
Donncha, I'm sure we'll be happy to answer any questions.
Have you considered using modern membrane separation techniques for separating water from your various solids? You have several processing steps where membrane separations could reduce energy costs.
They could. It wasn't part of the remit of the project, so it's not something that we've looked at. Our main focus was actually on the chemical conversion to levulinic acid. Actually modelling the processes was something that we did towards the end of the Dibanet proposal, and obviously now we've identified that this is a key area in terms of the economics of the process, is how do you actually recover the levulinic acid from the process stream. And we have some ideas. I suppose if you look at it, membrane filtration is one, and then the other one is centrifugal separation. There are probably better solvents out there than MTA jet to do centrifugal separation. But I don't especially have an expertise in membrane filtration, so it's not something that I would be qualified to understand, but certainly it's something that we would need to look at going forward.
Right. I see you've got seems like you've got a very, very efficient process in terms of energetic.
The fact that you're developing your equipment and this is going to be much more efficient. What about in terms of capital cost of all this new equipment?
Yes, this is, as I said, this is very recent in terms of the modelling. We haven't actually modelled the capital cost. There's another partner in the project that's doing that element. Our purpose was just to look at the mass and energy balances. But one of the key things that when we looked at what was the best way to improve, one of the, I suppose, the limitations in what was there when we started was that they're very high pressure reactors. You have a lot of sulfuric acid, so these reactors generally have to be made out of fairly exotic alloys. Some of them tantalum, as alloys, 310 stainless steel, and because of the pressures that they operate at, not for the plug flow system obviously, but definitely for the CSTR, you have a natural upper limit in terms of scalability. So what we have done in our process is we've tried to reduce the pressures and reduce the temperatures so that we could actually operate with ordinary stainless steel and kind of, for the most part, try and use materials that or reactor sizes that we could get off the shelf. So we expect that the capital cost when we have the analysis finished will be much significantly lower in terms of our process versus the old process.
Can you tell us what was the yield improvement in the acid production with respect to the number of CSTRs?
22%.
Going from 1 to 3 or?
Going to the residence time that was required to give it the same, to give 70% theoretical yield. So the 50% mass yield from biomass is 70% theoretical yield on a molar basis. And the real improvement was in terms of energy reduction and in terms of throughput. Because we're using less solvent, then obviously the amount of solvent that you're evaporating through the columns and the amount of solvent you're reheating back up to process temperature through the recyclers is significantly reduced. So, but we did have a 22% increase in levulinic acid yield. And the overall reactions from cellulose to levulinic acid, I suppose you could model the system in a very simple way. There is a series of consecutive reactions with various intermediates, but ultimately it boils down to your cellulose will either form these carbonaceous humic materials or your cellulose will form levulinic acid. And if you model it as those two simple parallel reactions, the Arrhenius profiles are such that if you increase temperature, you will always favour the formation of the humic materials, whereas the levulinic acid is relatively faster, always relatively faster. Absolutely, at lower temperatures, obviously you're going to slow down your reactions, but in terms of the ratio of the rates, it's favoured at about 170 degrees C. You have a cutoff where they switch. So the levulinic acid will be faster at lower temperatures. So that's why we got an improvement in yield.
You increased basically the
Throughput and the yield.
as far as time for processing?
The hold-up time is connected mostly with actually the recovery of the solvents, but the residence time has increased by threefold. But it's threefold in a reactor system which can be scaled up.
Okay, I'd like to thank Donncha for his presentation.